In the last video, we defined what it means for a differential equation to be exact. And, well, what it means for a differential equation to be exact is if in differential form, which is when we have p of xy times dx plus q of xy times dy, if in differential form we have that the partial derivative of p with respect to y equals the partial derivative of q with respect to x, then by Clairaut's theorem, there must exist some function whose partial derivative with respect to x is p, and whose partial derivative with respect to y is q. I know this is all very abstract. In the next video, we're probably going to get into some examples of exact equations and how to solve them. But in this video, let's just continue onward with the theory and establish, now that an equation is exact, we know there is some function whose partial derivative with respect to x is p, and whose partial derivative with respect to y is q. How do we solve the differential equation? Now, the very first thing we're going to do is just make an observation about the total differential. So if we remember, the total differential is df of xy equals the partial of f with respect to x dx plus the partial of f with respect to y dy. Our differential equation was very similar to this. The differential equation we're trying to solve in differential form was this. Our differential equation was that some function, which I guess we can actually write, we could have written p of xy, but we can also write the partial of f with respect to x, because we know it's exact. We know this is going to be the partial of f with respect to x times dx plus the partial of f with respect to y dy. If it's exact, it equals 0. And what this tells us is, obviously, this equals this, so we can equate if a equals b and b equals c, then a equals c. That's transitivity for you. So if we know these two things, then we also know that df equals 0. And if the derivative of our two variable function equals 0, then this tells us that our two variable function f of xy must equal a constant, c. And this is going to be our starting point for, now that we know what an exact equation is, we know that there exists some kind of a function that is going to construct the differential form that we had. Well, if we can find that function, we know that the solutions to the differential equation are going to be setting this function equal to a constant. So if we know what these solutions are, if we knew what the function was, the only next step is to find what f of xy is. So we've got to find f of xy. And we have a couple of ways we could think about this. The first thing we could do is we could notice, okay, hey, we have this differential equation here, partial f partial x dx plus partial f partial y dy equals 0. And we also have this total differential here, that the partial, not the partial, but just df, just regular derivative, is the same function, p of x times dx plus q of x times dy. Well, if we're trying to solve for f, maybe a good step to take would be to integrate this left side so that we get f. So if we have this here, we can say that the integral of df of xy, or just df in this case, that this is going to equal the integral of this right side. Okay, integral of the partial of f with respect to x dx plus partial of f with respect to y dy. Okay, this is actually not really a so useful way to do it, because, I mean, what do we even mean with this dx and the dy here? What a more fruitful way might be to say, okay, instead of this, let's just delete that, we have two constraints that f must satisfy. We know that the partial of f with respect to x equals our function p of xy, and that the partial of f with respect to y equals q of xy. Okay, well, given these two constraints, we should be able to solve for the function f. Let's think about how we might do that. Well, now is a much better time to integrate, because we can integrate this and actually get an answer that is sensible, because we can multiply by the partial x here and get that partial f equals p of xy times the partial of x. Whoops. Whoa, let's just rewrite that. Times the partial of x. And now if we integrate this, this actually makes sense. All right, so this seems like a better path to go down. And if we end up actually integrating this, we're going to get that, well, the integral of partial f, that's just going to be f of xy. Well, okay, we have our function here. It's equaling something. It's going to equal the integral of p of xy dx. Okay, so integral of p of xy dx, and this is partial x I should be doing. Partial x. And plus some constant, maybe? Not quite. Because we are taking this with respect not to dx, but partial x, because it's an entire multivariable function here, we would have to think we might not just be missing a constant, we might be missing an entire function of y. Because when we take the derivative with respect to x, so what I'm saying is if we took the derivative of some function with respect to x, not only would constants go away, really any function h of y, if we took the derivative with respect to x, this entire thing would disappear. So then if we took the integral of this derivative, we would have to say not only is this, because this is going to equal 0, if we took the integral, not only is this going to be some constant, it's actually going to be an entire function of y that we might be missing when we take the integral. So we can say instead of a constant of integration, we're going to have an entire function of integration, h of y. All right, let's delete this and make some space. Whoa, I deleted a little bit too high. Let's try that again. Not quite everything. Okay, perfect. So we know that f is going to be this integral plus this function of integration, the entire function, because any function of y could disappear. Okay, that's fine. Now, we still don't really know this because we can easily calculate what this integral is. That's great. But what in the world would this function of integration equal? Well, to figure that out, let's use our second constraint, which is that partial f partial y must equal q of xy. So if we take the partial derivative with respect to y of both sides of this equation, what we're going to end up with is that f sub y is going to equal the partial derivative with respect to y of the integral of p of xy partial x plus, and then the integral, the derivative with respect to y of h of y, that's just going to equal h prime of y. If we have all this, then we can say that the derivative of our function h of y, this function of integration, the derivative of that function is going to be the partial derivative of f with respect to y, which we can remember that's just q of xy, so we can replace this with q of xy minus the partial derivative with respect to y of the integral of p of xy dx. And with all of this set in place, we now have a satisfactory answer to what f of xy might be. Because we have f of xy up here, we know what this integral of p of xy with respect to x is going to be. We don't know what h of y is going to be, but we can just integrate this expression down here to find h of y, and everything is in terms of q of xy and p of xy, which are knowns. So, to clarify and to just recap what we've done, we now know, to write it out, that we have our function that we were searching for. Find f of xy. All right, we did that. F of xy equals the integral of p of xy with respect to x plus some function of integration, because any function of y could disappear, h of y. And what we know about this function is that h prime of y, so the derivative of this function of integration, and we can work backwards to get the function, is equal to q of xy minus the partial derivative with respect to y of the integral of p of xy dx. And given these two facts, we would be able to analytically solve for f of xy, and it's most likely actually going to be an implicit function now. Very rarely you'll get an explicit function. Now that we know what f of xy is, we have to be careful. We don't want to just box our answer, f of xy. We have to remember what we're doing. We're solving a differential equation. And in order to solve that differential equation, we have to remember this total differential up here. Our differential equation tells us that the total differential of f equals 0, which, we remember, told us that f of xy equals c is a solution to the differential equation. So now that we know what f of xy is, the solution that we want to box is the following. F of xy, which we hopefully just solved for, equals some constant c. This is our solution. Let me draw a nicer box. That is our solution. And still though we're quite abstract right now. We aren't concrete, and for that reason in the next video, I'm going to do an example, and hopefully you'll see, even though we're throwing around partial derivatives left and right here when we're developing what it might mean to solve an exact differential equation, once we start with an example, I hope it'll become much more clear how you actually solve one. And it isn't all that bad because you don't have to end up carrying all these terms because each of these is going to simplify out. So with that, I'll see you in the next video.